Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of gravitational fields. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics style examination questions, assess your understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out. Now in the right hand side section, write down any pieces of information which you find useful or any hints and tips on answering questions from the revision session. After the revision session concludes, write up these notes into a revision sheet for you to use independently. How should you be revising for A-Level AQA Physics? Well, firstly, you should be learning the key facts, so use revision guides, class workbooks, student prep notes and the textbooks to learn the key ideas of the course. Then test yourself. Use the Caboodle Knowledge Platform, the Seneca Learn Platform, the Student Knowledge Checker to quickly test your own knowledge. Finally, practice exam-style questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. So the three steps of preparing for the exams are learn the key facts, testing yourself and practicing exam-style questions. So, what are the key facts concerning gravitational fields? Well, we have Newton's law of gravitation. That's the idea that gravity is a universal attractive force between all masses. Newton's law of gravitational attraction is F equals g m1 m2 over r squared, where F is the gravitational force, g is the universal gravitational constant, m1 and m2 are the mass of the objects, and r is the distance between the centres of mass. The gravitational field strength is important as a gravitational field is represented by gravitational field lines. The gravitational strength is equal to G equal F over m, and in a radial field G is equal to G big M over r squared. Now for gravitational potential, that is the potential energy per unit mass. V equals minus gm over r, and the negative sign shows the attractive nature of gravity. The gravitational potential difference is the work done is equal to mass times by this gravitational potential difference. Now in equipotential surfaces, no work is done moving along them, and in our relationship between G and V, G is equal to minus the change in V over the change in r. So this indicates to us that the gravitational potential difference is equal to the area under a graph of G against r. Now for the orbits of planets and satellites we use Kepler's third law, which is t squared is directly proportional to r cubed for circular orbits. The escape velocity is the minimum speed needed to leave a gravitational field, and the energy of an orbited satellite is equal to the kinetic energy plus the potential energy, but the total should always be a negative because it's bound in an orbit around another object. Now to work out the kinetic energy we use a half mv squared, and for the potential energy we use minus gmm over r. Now, that tells us that potential has to be a negative energy. Now, for synchronous orbits, that is when the orbital period will equal the planet's rotation, whilst a geostationary orbit is the special case of a synchronous orbit around the equator of the planet. So let's just test our knowledge and understanding on gravitational fields. From this image, how can you tell that object 2 is experiencing a gravitational force? Pause the video now, then unpause the video when you want to go through your answer. Well, object 2 is experiencing a gravitational force as is inside the field of object 1. Next question, how can you tell that object 1 is experiencing a gravitational force? Object 1 is experiencing a gravitational force as is inside the gravitational field of object 2. What can be said about the size and the direction of the gravitational forces acting on object 1 and object 2? Well, the gravitational force experienced by each object is the same magnitude. The gravitational force experienced by each of them is moving them together. It's an attractive force. Will the acceleration experienced by each object due to being in the gravitational field be the same, and why? No. Each object will experience different acceleration, as whilst the gravitational force they experience is the same, their masses are different. Remember, acceleration is equal to resultant force over mass. Will object 2 or object 3 experience the greatest gravitational force from object 1 only, and why? Object 2 will experience the greatest gravitational force from Object 1 as it is closer to Object 1 than Object 3 is. Which object, Object 2 or Object 3, will experience the greatest gravitational force from Object 1 only, and why? Object 3 will experience the greatest gravitational force from Object 1 as it has more mass than Object 2, even though they are the same distance away from Object 1. From a field diagram, how can you determine the gravitational field strength of a gravitational field? The gravitational field strength can be represented by the density of the gravitational field lines. From a field diagram, how can you determine the direction of the gravitational field strength of a gravitational field? The gravitational field strength direction is represented by the direction of the field lines of the gravitational field. In this diagram, what object is producing the gravitational field, which we can then measure its gravitational field strength of? The gravitational field is being produced by the mass of object. In this diagram, which object is being affected by the gravitational field? The test mass is affected by the gravitational field. So in this diagram, which test mass is in a region of greater gravitational field strength, and why? Both test masses are experiencing the same gravitational field strength, as they are both the same distance away from the centres of mass in the gravitational field. The mass of object dictates the size of the gravitational field strength. Which test mass experiences the greater gravitational force, test mass 1 or test mass 2, and why? Test mass 2 will experience the greater gravitational force. This is because test mass 2 and test mass 1 are the same distance from the mass of object, yet test mass 2 has the greater mass. Where is the gravitational field strength the greatest value in the field, and why? The gravitational field strength is the greatest at the point mass. This is because the field density is the greatest here, and all the mass produced in the field is here. When is the gravitational field strength the greatest for a massive object, and why? The gravitational field strength is the greatest at the surface of the massive object. This is because it is the closest you can get in a gravitational field before there is a mass above the object producing a gravitational field in the opposite direction. So, what is the gravitational field strength at the centre of the Earth, and why? The gravitational field strength at the centre of the Earth is 0. This is because at the centre there is an equal amount of mass above and below that point. They are producing gravitational fields equal in size and opposite in direction. This gives a field strength of 0. So what is the gravitational potential at the centre of the Earth, and why? The gravitational potential at the centre of the Earth is 0. This is because at the centre there is an equal amount of mass above and below that point. They're producing a gravitational field equal in size and opposite in direction. They cancel through to give a potential of 0. When does the object have the greater magnitude of gravitational potential? Position 1 or position 2, and why? The object has the greatest magnitude of gravitational potential at position 1, as it's feeling a greater attraction due to gravity from the Earth as it's closer. When does the object have the greater value of gravitational potential, position 1 or position 2, and why? The object that has the greatest value of gravitational potential is at position 2, as the gravitational potential is always a negative value, so it is at a higher negative value at position 1 compared to position 2. Apart from at the centre of the Earth, when will the object experience no gravitational potential, and why? It will be when the object is outside of the gravitational field of the Earth, as it's no longer feeling an attraction to the Earth. Is work done to move the object from position 1 to position 2, or from position 2 to position 1, and how can you tell from the diagram? Work is done when the object moves from position 1 to position 2, as it's moving against the field lines of the gravitational field. Will object 2 or object 3 have the largest magnitude of gravitational potential from object 1 only, and why? Both objects will have the same gravitational potential as each other as they are the same distance away from the centre of object 1. Will object 2 or object 3 have the greatest magnitude of gravitational potential from object 1 only, and why? Well, both objects will have the same gravitational potential as each other, as they're the same distance away from the centre of object 1. Will object 2 or 3 have the largest magnitude of gravitational potential energy from object 1, and why? Object 3 will have the greater gravitational potential energy, as even though they have the same gravitational potential, object 3 has the greater mass, so will therefore have the greater gravitational potential energy. Is work done to move the object from position 1 to position 2, or position 2 to position 1, and how can you tell from the gravitational potential? Well, work is done when the object moves from position 1 to position 2 as it's moving between two areas of different gravitational potential. Where will the energy come from to change the gravitational potential energy store of the object as it moves? The energy comes from the kinetic energy store of the orbiting body. In which position will the object be orbiting slower, position 1 or position 2, and why? The object will be orbiting slower in position 2 as more of the total energy can be found in the gravitational potential store, not the kinetic store. Will the object carry out any work in moving from position 1 to position 2, and why? No work is carried out moving from position 1 to position 2 as it's not moving to areas of different potential. How can the Moon orbit the Earth successfully with no work being done? The Moon orbits the Earth without any work being done as it's in an orbital plane, which is a plane of equipotential. Is work needed to be done to put a satellite into orbit? How is this achieved? Yes, work is needed to be done as the satellite is moving between areas of different gravitational potential to do this. This is achieved with the use of thrusters. Is work needed to be done to keep a satellite in orbit? No work is needed to be done as the satellite moves in orbit as it will move in a plane of equipotential. Which satellite experiences the greater gravitational force from the Earth and why? Satellite 1 experiences the greater gravitational force from the Earth as there's a smaller separation between the Earth's centre of mass and its centre of mass. Which satellite is travelling at the higher orbital velocity, assuming a stable orbit? Satellite 1 is travelling at a higher orbital speed as it's experiencing a greater gravitational force. Which satellite will complete an orbit in a quicker time period and why? Satellite 1 will complete an orbit in a faster time period as it's travelling faster, so has less distance to cover in one orbit. In terms of gravitational potential, how can a satellite maintain a constant orbit? The satellite will maintain a constant orbit if it's on a sphere of equipotential. The satellite moves from position 1 to position 2. Both positions are in a circular orbital path. What happens to the total energy store of the satellite? The total energy store of the satellite remains constant. The satellite moves from position 1 to position 2. What happens to the kinetic energy store of the satellite and why? The kinetic energy store of the satellite decreases as the satellite is now moving slower. The satellite moves from position 1 to position 2. What happens to the potential energy store of the satellite and why? The potential energy store of the satellite increases as it's now closer to leaving the field. How can the potential energy store of the satellite increase as it's moving closer to the edge of the field? The potential energy store of the satellite when it leaves the field when it's at infinity is 0, so it starts off negative and becomes less negative or more positive and increases as it moves towards the edge of the field. In an elliptical orbit, what will happen to the speed of the satellite throughout its orbit. The satellite will increase in speed as it's getting closer to the Earth, and then decrease in speed as it moves away from the Earth. Let's have a look at some examination style questions for gravitational fields. A space probe is sent to investigate a previously uncharted planetary object. The scientists collect the following data. The data are measured when the probe is in freefall towards the planet. Using the data, deduce whether the object behaves as a point mass or as a significant mass distribution above the measured radius. Without further calculation, explain how you could use the graph of G against R to estimate the gravitational potential difference between 8,000 km and 2,000 km from the planet's centre. Assuming the gravitational potential at 8,000 km is minus 1.56 times 10 to the 7 joules per kilogram, estimate the potential at 2,000 km. Comment on the significance of the negative value and what this tells us about the gravitational energy. The probe moves from 8,000 km to 2,000 km. A student suggests that no energy is transferred because gravitational fields do the work automatically. Comment on this statement. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, if it is a point mass, then G should follow the inverse square law. So when the distance doubles, it should then quarter. Now you should compare this with other values as well, so you can look at this and the relationship holds. So the field does behave like that of a point mass. The mass is concentrated within 2,000 kilometers. Now the potential difference is the area under the G against R graph. So from the 8,000 kilometers to 2,000 kilometers, the area under the curve will give you that change in potential, gravitational potential. Now the potential is more negative closer to the mass. So therefore, if we know it's minus 1.56 times 10 to the 7 joules per kilogram at 8,000 kilometers, well then you could then divide that again by 4 because we're now going to 4 times closer, so it's minus 6.25 times 10 to the 7 joules per kilogram. Now the negative sign means that the gravitational potential is relative to 0 at infinity. So this indicates to us that we must be given energy to it to escape the gravitational field. Now, as it goes from 8,000 kilometers to 2,000 kilometers, the probe gains kinetic energy as it falls, so an energy transfer occurs. Now, the gravitational potential energy will decrease, it will convert to kinetic energy, so the field is doing work on the object, just that there's no fuel or propulsion needed. A group of aerospace engineers are evaluating the theoretical design of a space elevator, a long cable extending from the Earth's surface to a station in a geostationary orbit at 36,000 kilometers above the equator. Cargo will be lifted along the cable using electric motors rather than rockets. They use a model of the Earth where the gravitational field behaves as a radial for distances greater than 100 kilometers above the surface. Explain why the gravitational potential is a negative and why its magnitude decreases with an increasing distance from the Earth's centre. The energy required to lift a 500 kilogram cargo from the Earth's surface to the space station is estimated using gravitational potential values. The team claims that the energy is less than that required by a chemical rocket. Is this true? Then a student suggests that once the elevator reaches 36,000 kilometers, no further energy is required to keep it in place. Comment on this statement. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, gravitational potential is defined as 0 at infinity. A negative value shows that work must be done against the gravitational field to move the mass to infinity. As the distance increases, the gravitational attraction weakens, so the potential becomes less negative. We know that work done is equal to mass times by the gravitational potential difference, so it's only dependent on the gravitational potential difference. Now, rockets must also provide energy for kinetic motion, for fuel, and overcoming air resistance. Now, the elevator supplies only gravitational energy, so it's more efficient. So the claim is a reasonable one, provided that any losses to their surroundings, such as friction, are minimal. Now, objects in geostationary orbits must travel at a constant tangential speed, so it remains in orbit due to the balance between the gravitational force and the centripetal force. So the cable tension provides this force rather than a continual propulsion, so no energy is needed to stay in orbit, but a constant tension is. A satellite of mass 750 kilograms is to be lifted from the surface of the Earth to a low Earth orbit at a height of 300 kilometers above the surface. The radius of the Earth is 6.37 times 10 to the 6 meters per second, and the mass of the Earth is 5.97 times 10 to the 24 kilograms. Calculate the gravitational field strength at the surface of the Earth and at a height of 300 kilometers above the surface. Determine the gravitational potential of both positions and hence calculate the energy required to move the satellite from the surface to this orbit. The launch team want to minimize fuel usage. Based on your result for part A 1.2, discuss whether the majority of the energy is spent on overcoming the Earth's gravity or achieving orbital motion. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know at the surface G equals gm over r squared. Pop in our numbers and we get 9.8 newtons per kilogram. We now do the same at a height of 300 kilometers. So we now add the height of 300 kilometers to the radius of the Earth, all in meters. So we then get our answer to be 8.95 newtons per kilogram. Again, at the surface, it's V is equal to gm over r. We use our same values for r in the previous question. So we can pop it all through and we get minus 6.26 times 10 to the 7 joules per kilogram and minus 5.97 times 10 to the 7 joules per kilogram. So our work done is our mass times by our change in gravitational potential, which is 2.18 times 10 to the 7 joules. So this tells us that the energy required to lift a satellite is 2.18 times 10 to the 7 joules. But the orbital kinetic energy at 300 kilometers is much higher. It's about 2.5 times 10 to the 9 joules. So therefore, most of the energy is required for achieving orbital velocity, not lifting it against gravity. A newly discovered exoplanet called Trion has a moon named Lyraea. Astronomers observe that Lyraea maintains a stable circular orbit at a radius of 5.6 times 10 to the 7 meters from the center of Trion. The orbital period of Lyra is measured to be 2 times 10 to the 5 seconds. So, calculate the mass of the planet Trion, determine the orbital speed of the moon Lyraea, and calculate the total mechanical energy of the moon in its orbit, assuming its mass to be 1.5 times 10 to the 16 kilograms. Another moon, Lysara, is discovered to orbit Trion with an orbital period of 5 times 10 to the 5 seconds. Use your result from A 1.1 without further calculation to deduce whether Lysara orbits closer or further from the planet than Lyraea. Explain your reasoning. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, we can rearrange the equation which comes with Kepler's third law of orbital motion to say m is equal to 4 pi squared r cubed over gt squared. Pop in all the values, and what you work it through is m is equal to 3.09 times 10 to the 24 kilograms. We know that v is equal to 2 pi over t. So when we work this all through, when we work out our value, we get it to be 1.76 times 10 to the 3 meters per second. Now we know the kinetic energy is going to be half mv squared, which is working it all through to be 2.33 times 10 to the 22 joules. We know that the gravitational potential energy is minus gmm over r, so we get that to be minus 4.66 times 10 to the 22 joules. We add the two total together and we get minus 2.33 times 10 to the 22 joules. Now, we know from Kepler's law that t squared is directly proportional to r cubed. So we know that the t of Lysara is greater than the t of Lyraea. So that indicates to us that the radius of orbit for Lysara must be greater than the radius of orbit for Lyraea. So this tells us that Lysara orbits further away. So the longer orbital period has led from our larger orbital radius. A satellite engineering firm is tasked with selecting an orbit type for a new disaster monitoring satellite. The satellite must provide regular, high-resolution imaging of all regions of the Earth, operate with minimal launch and maintenance costs, support real-time communications in emergencies. Now the firm compares 3 different orbit types. Using the table, explain the relationships between the orbital radius and the period. What does this suggest about the nature of the gravitational force acting on the satellites in different orbits? Evaluate the trade-offs between the LEO and GEO for this disaster response satellite, and conclude which orbit type you would recommend. Justify your answer. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, as you can see, as the altitude or radius increases, the orbital time period will increase as t squared is proportional to r cubed. Now, the gravitational force is providing our centripetal force in this case, so F equals gmm over r squared. So this indicates to us that there's a weaker gravitational field at higher altitudes, so the satellites will move more slowly, leading to the longer time period. Now, the LEO has a short time period, so revisits regions frequently, which is good for monitoring rapid events. The LEO provides higher resolution imaging as it's closer, but the GEO provides continuous coverage of one region, which again is useful for real-time responses. The LEO will need more satellites for full coverage, so you need a higher network. So the GEO satellites will also be more expensive to launch as they go into a higher orbit. Now, finally, I would recommend the LEO for frequent global imaging. It's justified by its lower altitude to give better resolution as there's less diffraction and signal delay, and the shorter time period means a quicker revisit, so you'll get more up-to-date information on the disaster. Although more satellites would be needed, the system is possible and the launch costs for each one will be lower. A space agency is evaluating the possibility of constructing a manned research station on a moon orbiting the exoplanet Kepler-62f. The moon has been observed to orbit Kepler-62f with the following parameters. Orbital radius of the moon is 2.5 times 10 to the 8 meters. The orbital period is 1 times 10 to the 6 seconds. The moon itself has a radius of 3.2 times 10 to the 5 meters and a mass of 4.70 times 10 to the 22 kilograms. A spacecraft will need to land on the moon and later escape its gravitational influence to return to Kepler-62f's orbit. Use the moon's orbital radius in period to estimate the mass of Kepler-62f. Calculate the gravitational field strength and the escape velocity at the surface of the moon. Then hence assess whether a conventional chemical lander, capable up to 2.6 kilometers per second, could leave the moon after landing. The agency claims that setting up the station on a moon is low risk in terms of energy requirements for orbiting, landing and leaving. Use your results and understanding of gravitational potential and energy to critically evaluate this claim. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one we know m is equal to 4 pi squared r cubed over gt squared. We pop in all the numbers given to us in the question and we can work it out to be 9.3 times 10 to the 24 kilograms. Next one. We know g is equal to g equals gm over r squared to work out the gravitational field strength. So we can work it out when we pop in all the values to be 3.1 newtons per kilogram. We then know that v is going to be equal to the square root of 2gm over r. So we work it all through, pop in all the values, and we get our answer out to be 2.80 kilometers per second. Now, when we compare this with the capacity of 2.6 kilometers per second from the chemical lander, it's not sufficient. So it couldn't actually be greater than the escape velocity we've just previously calculated. So therefore, the standard lander cannot escape. Finally, the energy for orbiting around Kepler-62f is large due to the large orbital radius and host mass. So the landing energy cost is moderate as g is lower than on Earth, but it's not nothing. Now the escape velocity exceeds the capability, so we'll need something else to provide alternative propulsion or fuel. Now the gravitational potential implies a large energy is required to leave, so the conclusion is it's not low risk, especially due to the escape energy. The mission would need a greater propulsion system than the one that it has already. The moon has an orbit around the Earth of radius 3.86 times 10 to the 8 meters with a time period of 2.36 times 10 to the 6 seconds. Using the data provided, show that the product gm is about 4.1 times 10 to the 14 meters cubed seconds to the minus 2, where m is the mass of the Earth. At the surface of the Earth, g is measured to be 9.81 newtons per kilogram. Calculate a value for the radius of the Earth. It has been estimated that at any one time there may be about 1,000 small asteroids orbiting the Earth. These asteroids orbit between 5 to 10 times the distance of the Moon from the Earth. Most make no more than one orbit before being pulled out of this orbit by the Sun. Suggests why these asteroids do not remain in a stable orbit around the Earth. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, we know omega is equal to 2 pi over t. So it's 2.66 times 10 to the minus 6 radians per second. We know gmm over r squared equals m omega squared r, as the centripetal force is the gravitational force. So at that point, we can work out gm to be equal to omega squared r cubed. Pop in the value, we get 4.07 times 10 to the 14 meters cubed seconds to the minus 2. We know g equals gm over r squared, so r is equal to the square root of gm over g. Pop in all the values, 6.44 times 10 to the 6 meters. Now, the force will vary from the distance of the Earth, so according to the inverse square law, F is proportional to 1 over r squared, so the force on these asteroids will be very small. The gravitational potential between the Earth and the Moon due to the combined effect of their gravitational field increases to a maximum value of minus 1.28 megajoules per kilogram at a point between them. Calculate the minimum speed at which a rock would have to leave the Earth in order to reach the Moon. In your calculation, you may assume that the rock has zero kinetic energy when it has a maximum potential energy. The mass of the Earth is 5.97 times 10 to 24 kilograms, and the radius of the Earth is 6,370 kilometers. 4 billion years ago, the Moon had a different orbital period because it was closer to the Earth than it is today. Calculate the period of the Moon's orbit 4 billion years ago when the radius of its orbit was 1.34 times 10 to the 8 meters. So, pause the video now, then unpause the video when you want to go through your answer. Right, we know that V is equal to minus gm over r. So you pop in all the values, convert the kilometers into meters, and we get minus 62.5 megajoules per kilogram. The change in gravitational potential is the Moon's gravitational potential minus the Earth's gravitational potential. So we get minus 61.2 megajoules per kilogram. So we know m delta V is equal to the kinetic energy, or a half mv squared. So that tells us, by cancelling out the m's, a half v squared equals 61.2 megajoules per kilogram. So V equals 11,100 meters per second. We also know in this case that the gravitational force is the centripetal force, so gmm over r squared is equal to mv squared over r. So therefore gm over r squared equals v squared over r. We know that v equals 2 pi r over t. So therefore t squared is equal to 4 pi squared r cubed over gm. Pop in our values, we get 2.38 times 10 to the 11 seconds squared, square root that, 488,000 seconds, which is 5.7 days. Makemake is a dwarf planet in the solar system. Makemake has a mass of 3.1 times 10 to 21 kilograms and a radius of 715 kilometers. Calculate the gravitational field strength at the surface of Makemake. The average distance of Makemake from the Sun is similar to the average distance of the dwarf planet Pluto from the Sun. A website states that the time taken by Makemake to complete one orbit of the Sun is 20% greater than the time taken by Pluto to complete one orbit of the Sun. Assess the accuracy of the website statement. So, pause the video now, then unpause the video when you want to go through your answer. Right, we know G is equal to gm over r squared, pop in all the values, and we get 0.404 newtons per kilogram. We know that omega is equal to the square root of gm over r cubed. Pop in all the values, and omega is equal to 6.5 times 10 to the minus 10 radians per second. T is equal to 2 pi over omega, so that equals 9.67 times 10 to the 9 seconds, which is 307 years. So our orbital time ratio between Makemake and Pluto is 1.24. So therefore the orbital time period of Makemake is 24% greater than that of Pluto, so the website statement is not quite accurate. So that brings an end to our revision session today. If we've been successful in our revision session, we can answer A-Level Physics exam style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So, thank you so much for watching this particular video, which has been on gravitational fields, which is part of AQA A-Level Physics Paper 2. Thank you so much for watching and have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of gravitational fields. So in today's lesson we're going to be looking at how to answer examination questions for AQA A-Level Physics Paper 2, in particular gravitational fields. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions for gravitational fields, assess our understanding on A-Level Physics gravitational fields, and then finally understand what topics we need to improve upon for AQA A-Level Physics Paper 2, in particular gravitational fields. So how should you prepare for this revision session? Well, when you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and your answers to the questions in this revision session. When you're doing this, try to make sure you're writing full sentences and show your full working out. Whilst on the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, in terms of revising AQA A-Level Physics, what should you be doing? Well, the first step is learning the key facts, so use your revision guide, class workbook, student prep notes and the textbooks to learn the key ideas of the course, which might include writing mind maps or notes for yourself. The second step is to do retrieval, so test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this using your own cue cards. Then finally, you can do practice by practicing examination style questions, so use things like exam practice books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you may wish to download your own exam past papers to do this. So the three steps of learn the key facts, then testing yourself, and then practicing your examination questions are how you should be revising for your A-Level Physics. Now, in this revision session, you'll find we have three types of questions. The first question is a general check question. So these are the basic questions designed to probe your understanding of the key concepts of the topic. The second type of question are the checkpoint questions, which are more challenging questions designed to place your knowledge and your understanding of the topics into different contexts and applications. Whilst the third type of question are the assessment point questions. So these are past paper examination questions which will mimic the type of questions which are found in public examinations. So let's now start having a look at the gravitational fields topic. So the first question says, describe what happens to the gravitational force between two objects A and B when the mass of A doubles, then the mass of both A and B double, then the distance between A and B halves, and then finally the mass of B doubles and the distance between A and B decrease by a factor of 4. So pause the video now, then unpause the video when you want to go through your answer. Right, so this is a test of the Newton's law of gravitation, where F equals gmm over r squared. So this tells us that F is directly proportional to m, so therefore that relationship would hold that if m doubles, F doubles. Now we know again from Newton's law of gravitation that F is directly proportional to mm, where they're both the masses of the two objects. So if big M and small m double, well therefore both will double, so therefore be times by a factor of 4, so F will quadruple. We also know from the law of gravitation that F is directly proportional to 1 over r squared. So of r halves, F will therefore quadruple because it's half squared, so it's a quarter, then 1 over a quarter is times by 4, which is a quadrupling. Now if we link them all together, that F is directly proportional to m and F is directly proportional to 1 over r squared, well when m doubles, F doubles, and if r decreases by a factor of 4, F increases by a factor of 16, so that therefore means F will increase by a factor of 32. The next question says, calculate the gravitational force between two protons of mass 1.67 times 10 to the minus 27 are separated by a distance of 1 times 10 to the minus 14 meters. Two students of mass 65 kilograms and 70 kilograms standing 1.5 meters apart, and then Saturn and the Sun, where you got the mass of Saturn there, the mass of the Sun there, and their average separation in kilometers. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, this is using Newton's law of gravitation, where F is equal to gmm over r squared. So in this first one, you pop in all the values. Now again, remember it's r squared, and then you get out your answer to be 1.9 times 10 to the minus 36 newtons. Again, you pop in these values, F equals gmm over r squared. Again, remember to square r. So we get 1.3 times 10 to the minus 7 newtons. And then here in this question, remember that you're given the separation in kilometers, and we work in meters in A-Level Physics for this particular equation. So you've got to convert million kilometers into meters, so it's 1,400 times by 10 to the 9. So therefore the answer is 3.8 times 10 to the 22 newtons. The next question says, state the effect on the gravitational field strength at a point in a radial field around a point mass when firstly, the mass of the point mass is created in the field is halved, the distance from the point mass increases by a factor of 3, and then the mass of the point mass decreases by a factor of 4 and the distance from the point mass halves. Then explain why when moving an object from a height of 100 meters to a height of 200 meters above the surface of the Earth, the gravitational field strength does not decrease by a factor of 4. So pause the video now, then unpause the video when you want to go through your answer. Right, so again we're looking at our equation for gravitational field strength. So gravitational field strength is equal to gm over r squared. So therefore g is directly proportional to m. So if m halves, g will halve. G is then proportional to 1 over r squared. So if r increases by a factor of 3, g will decrease by a factor of 9 because it's 3 squared. And then we link the two ideas together. So if g is directly proportional to m, if m decreases by a factor of 4, g will decrease by a factor of 4. And g is proportional to 1 over r squared. So if r decreases by a factor of 2, g will increase by a factor of 4, 2 squared. So the two things will cancel out, so there'll be no overall change in the gravitational field strength. Now we do know that g is directly proportional to 1 over r squared, but it's a very important idea to remember that r is measured from the center of mass of the object, not the surface of the object. So in fact moving from 100 meters above the surface to 200 meters above the surface does not double r because it's not being taken from the center, so that's why it doesn't decrease by a factor of 4. The next question says, the Sun has a mass of 1.99 times 10 to the 30 kilograms and a diameter of 1.39 million kilometers. Calculate the gravitational field at its surface. Then calculate the gravitational field strength 1.2 times 10 to the 8 meters from a point mass of 2.6 times 10 to the 23 kilograms. Then Mars has a mass of 6.42 times 10 to the 23 kilograms and a surface gravitational field strength of 3.72 newtons per kilogram. Calculate the radius of Mars. Then the surface gravitational field strength of Venus is 8.77 newtons per kilogram and it has a radius of 6.09 megameters. Calculate the mass of Venus. So pause the video now and then unpause the video when you want to go through your answer. Right, so this is using the gravitational field strength equation where G equals big G, big M over R squared. So you pop in all the values there, remembering we're going to square R, and second remember it's million kilometers, so we're going to convert that into meters, so that'll be 10 to the 6. So therefore you would work it through, okay, to be, work it through there to be 679 newtons per kilogram. Now notice, by the way, we've been given the diameter, so we're going to have to halve that to work out what the radius is. The next question again, we're doing G, big G, M over R squared. Pop in all the values, work it through. Remember it's R squared, so you get 1.2 times 10 to the minus 3 newtons per kilogram. This next one, we're going to rearrange it to make R, the radius of the subject, so R is going to be equal to the square root of gm over small g. So therefore you pop in all the values, work it through and get 3.4 times 10 to the 6 meters. And then the next one, we're going to make an m the subject, so m is equal to gravitational field strength times by R squared over the gravitational constant. Pop in all the numbers, remember it's R squared, and remember we were given the radius in megameters, so mega is times 10 to the 6, so we get 4.88 times 10 to the 24 kilograms. The next question says, determine the gravitational potential at firstly the Earth's surface, then secondly at a height of 650 kilometers above the Earth's surface. Then a small space probe of mass 510 kilograms has been landed on the surface of a small asteroid. Determine the output energy of the probe's onboard rockets for the probe to escape the gravitational field of the asteroid, given that the gravitational potential at the surface of the asteroid is minus 40 kilojoules per kilogram. Then the gravitational potential at the surface of a planet of radius r is v. What will the gravitational potential at a height of r above the planet's surface be? So pause the video now, then unpause the video when you want to go through your answer. Right, again, so we've got to remember what our gravitational potential equation is. So the gravitational potential is equal to negative big G big M over the radius of the object. So therefore we pop it all through. Remember, you're given the radius of the Earth on the equation sheet. It's 6.37 times 10 to the 6 meters. Pop in all the values through, and it's negative 6.25 times 10 to the 7 joules per kilogram. The next one, we're going to have to add 650 times 10 to the 3, because we converted kilometers into meters, to the radius of the Earth's surface, because we take r from the center of mass of the object. So we've got to add the radius of the planet to the distance above the surface. We then pop in all the values, and we get minus 5.67 times 10 to the 7 joules per kilogram. This next one, we've got to remember that here the change in gravitational potential, okay, is going to have to be 40 times 10 to the 3 joules per kilogram. Now work done is equal to mass times by the change in potential. That again is another equation which you're given in the exam, but you've also got to be able to use. So the mass of the object that's being moved, not the mass of the object making the field. Remember, if it's small m, it's the mass of the object that's moving in the field. So it's 510 times by 40 times by 10 to the 3. So we get our answer out to be 20 times 10 to the 6 joules. The next question is, we know V is directly proportional to 1 over R. We can tell that from the equation V minus Gm over R. So if G and M are constant, V is directly proportional to 1 over R. So therefore, if the height is doubled above the if height is doubled, we can therefore say that it's going to be halved for the potential, because they're inversely proportional. The next question says, draw lines to show the shape and direction of the gravitational field of the Earth. Then the gravitational field strength G is uniform close to the Earth's surface. Describe the pattern of the gravitational field lines close to the surface of the Earth. Then the planet Saturn has a mass of 5.7 times 10 to the 6 kilograms and a radius of 6 times 10 to the 7 meters. Calculate the gravitational field strength at Saturn's surface. Then Saturn's second largest moon, Rhea, has an orbital radius of 5.3 times 10 to the 8 meters and a mass of 2.3 times 10 to 21 kilograms. Calculate Rhea's orbital speed, then calculate Rhea's kinetic energy. So pause the video now, then unpause the video when you want to go through your answer. Right, so this first one, you've got to be able to understand what a gravitational field looks like for a planet. So you're going to have radial lines coming out of the Earth, indicating they appear to meet at the center of the Earth. However, they would just stop at the surface of the Earth, but they would appear to actually meet at the center. And you got the direct towards the Earth, because the field lines show the direction in which a mass would move. Gravity is always attractive, so the field line should be going towards the planet or the object. And this next one, you would notice that if it's a uniform field, well, we can tell that gravitational field strength is shown by how close the field lines are together. So if it's a uniform strength, the field lines are staying the same distance apart from each other, so therefore they're parallel to each other and perpendicular to the surface of the Earth itself. Now, to calculate the gravitational field strength, we'll do G equals big G big M over R squared. Pop in all the values. Remember, it's R squared, and we get 11 newtons per kilogram. Now this next one, we can work out the orbital speed, because we can say that the equation for the orbital speed is V equals the square root of Gm over R. Again, that's worked through by looking at the energies, okay, of the particular of the object. So we can say V is equal to square root to Gm over R. You can pop that all through and you work it out to be 8.5 times 10 to the 3 meters per second. Now in terms of calculating kinetic energy, we can work out that with our equation. Kinetic energy is a half mv squared. The very famous equation still works in this context. So it's a half mv squared. We've just worked out V before, so therefore it's 8.2 times 10 to the 28 joules. The next question says, determine the mass of the Sun given that the time of orbit of the Earth is 365 days and the rate of the Earth's orbit is 1.5 times 10 to the 11 meters. The radius and time of the orbit of Io, one of Jupiter's moons, are 5 times 10 to the 4.22 times 10 to the 8 meters in 42 hours respectively. So determine the mass of Jupiter. Then it's estimated that the solar system completes an orbit around the galactic center of the Milky Way in 250 million years with a radius of orbit of 27,000 light years. Determine the effective mass within the orbit that has its center of mass at its galactic center. 1 light year is 9.46 times 10 to the 15 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this first one, we've got to use the concepts you've covered in circular motion, because the orbit will be considered to be carrying out a circular path. So we can say that the angular velocity is equal to 2 pi over t. So it's the angular change in one complete revolution, 2 pi radians, divided by the time taken for one complete revolution. That time must be given in seconds. You're going to have to convert the value of 1 year into seconds, because that is how long it takes for the Earth to orbit the Sun once. So you get out to be 1.99 times 10 to the minus 7 radians per second. We can then use our equation to work out the mass, because what we can do is we can link it in with the law of orbits that comes through, where we say that mass is equal to r cubed omega squared over g. We can pop in all the values and we get 2 times 10 to the 30 kilograms. That comes again from Kepler's law of orbits. The next one, again, it's the same principle once again. We can work out the angular velocity by doing 2 pi over t, work out our angular velocity in radians per second to be 4.16 times 10 to the minus 5, pop in the values into the equation to work out mass, and we get 1.9 times 10 to the 27 kilograms. And then again, same logic, omega is equal to 2 pi over t, work it all through, and we get 8.3 times 10 to the minus 16 radians per second, where you can work out the mass with our equation r cubed omega squared over g, pop in all the values, and we get 1.7 times 10 to the 41 kilograms. The next question says, calculate the orbital speed of the Hubble Space Telescope given that it orbits at a height of 547 kilometers above the Earth's surface, and then determine the radius of orbit and the altitude of a GPS satellite which orbits the Earth twice a day. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we've got to be able to work out orbital speed. So we're using our equation which we talked about before, where v is equal to the square root of gm over r. That's the equation for orbital speed. We can pop in all the values. Now again, remember that r is the distance we have from the center of the Earth to the actual satellite. So you've got to add the distance above the surface to the radius of the Earth. Once again, is given to you on the equation sheet. We work out our answer, and then 7.59 times 10 to the 3 meters per second. Now this next one, again, we've got to work out our angular velocity by doing 2 pi over t. Again, we know that it orbits twice a day, so therefore we can do 12 times by 3,600 for the orbital time, because there's 3,600 hours in 1 second, and it orbits once every 12 hours. So we get our answer to be 1.54 times 10 to the minus 4 radians per second. We can therefore work out r from the equation we looked at before, and we can get our r out to be 2.66 times 10 to the 7 meters. So that's the total separation from the center of mass to the actual satellite. We subtract then the radius of the planet, 6.37 times 10 to the 6, to get the actual height above the surface to be 2.02 times 10 to the 7 meters. The next question says, determine the kinetic energy of the SMAP satellite, which has a mass of 1,123 kilograms and orbits the Earth at a height of 685 kilometers. Then determine the kinetic energy of the Earth in its orbit around the Sun. Then determine the escape velocity of an object at the Earth's surface, and then determine the escape velocity of an object at the Moon's surface. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to remember is, how can you work out the kinetic energy? Well, the energy is going to be working through because it's actually going to be equal to the change in potential energy. So you can say E is equal to G big M small m over 2R. So we can pop those all in. Now again, we do know that kinetic energy equals a half mv squared, but we don't have enough information to work out V in this particular situation. So we can use GMM over 2R, which is the change in potential energy. Remember, R is the distance from the center of the Earth to the object, so we've got to add the radius of the Earth to the height above the surface of the Earth to work out our answer to be 3.17 times 10 to the 10 joules. The next question, again, we're using that same equation. The change in potential is equal to the kinetic energy, which is GMM over 2R. So therefore we can pop in all the values. Once again, remember, we're going to be able to work out it's the distance it is from the Earth to the Sun, which was given before to be 1.50 times 10 to the 11 meters. Again, that's given to you on the equation sheet. So it's 2.64 times 10 to the 33 joules. The escape velocity, now again, this is an equation which you'd have to memorize. Again, it comes from the energy transfers that go on. The kinetic energy equals potential energy. So the escape velocity is going to equal to be the square root of 2g gm over r. So whilst the orbital velocity is square root gm over r, the escape velocity is square root 2 gm over r. So you pop in all the values that we've got. Remember, r is going to be the radius of the Earth because we're at the surface of the Earth. We pop in all the values and we get 1.12 times 10 to the 4 meters per second. Then we can use the same equation to work out the moon's escape velocity by doing square root 2 gm over r, pop in all the values given to you in the question, and we get 2.37 times 10 to the 3 meters per second. The next question says, calculate the gravitational force of attraction between two objects separated by a distance of 1 centimeter, each having a mass of 100 grams, two asteroids separated by a distance of 4 times 10 to the 9 meters and each having a mass of 5 times 10 to the 10 kilograms, a satellite of mass 1.4 times 10 to the 4 kilograms orbiting the Earth at a distance of 6,800 kilometers from the Earth's center, and then estimate the gravitational force of attraction between two people sitting side by side on a park bench. How does this force compare with the gravitational force exerted on each of them by the Earth? So pause the video now, then unpause the video when you want to go through your answer. Right, so this one again, we're using Newton's law of gravitation. So F equals gmm over r squared. Remember, we don't work in centimeters, we work in meters. Okay, so you work it through to be 6.67 times 10 to the minus 9 newtons. Next again, we use the gravitational law of attraction. So we can then do gmm over r squared, pop in all the numbers, remember it's r squared, and we get 1 times 10 to the minus 8 newtons. The next question, again, we're using gmm over r squared. Now again, remember that we're going to be not working in kilometers, we're working in fact in meters, so it's 6.8 times 10 to the 6, okay, and it's r squared, and we get our answer to be 1.2 times 10 to the 5 newtons. Now it's very important that you can estimate values in A-level physics. So people are sitting side by side with each other, we say they're about 0.5 meters apart. We say they've each got a mass of about 70 kilograms, so you can pop that into the equation, and we get out about 10 to the minus 6 newtons. So a human with a mass of 70 kilograms will have a weight of about 700 newtons because it's mass times by gravitational field strength, which is 9.81. So we can say that their weight is greater than the mutual attraction by about a factor of like 10 to the 9. So it's very, very a much bigger idea of weight than it is gravitational attraction. The next question says, calculate the gravitational force between two pi-0 particles in deep space if they are 8 meters apart. The mass of this pi-0 or neutral pion is 2.4 times 10 to the minus 28 kilograms. Then calculate the gravitational force between the Earth and the Moon if the Moon's mass is 7.35 times 10 to the 22 kilograms. The distance from the Earth to the Moon is 384,400 kilometers. Then calculate the average distance of the Earth from the Sun if the Sun's mass is 2 times 10 to 30 kilograms. The gravitational attraction between the Earth and the Sun is 3.57 times 10 to 22 newtons. So pause the video now, then unpause the video when you want to go through your answer. So again, in this question, we're going to be using Newton's law of gravitation. F equals gmm over r squared. So you pop in all the values, you work it through, and we get 6.0 times 10 to the minus 68 newtons. This next one again, we'll be using that same law of gravitational attraction. F is equal to gmm over r squared, pop in all the numbers, and we get 2 times 10 to the 20 newtons. Always remember to be squaring the r value in that equation. And once again, we're now going to work the other way around. So we're using Newton's law of gravitational attraction, but we're now making r the subject. So r is equal to the square root of gmm divided by m there, so you work it through and you get 1.5 times 10 to the 11 meters by working all those values through. So it's square root of gmm over f. My apologies. The next question says, figure 18.14 shows the Earth's gravitational field. Copy the diagram and add arrows to show the direction of the field. Explain why the formula for potential energy gained, mg delta h, cannot be used to find the increase in potential energy when an aircraft climbs to a height of 10,000 meters, but cannot be used to calculate the increase in potential energy when a spacecraft travels from the Earth's surface to a height of 10,000 kilometers. Then Mercury, the smallest of the 8 recognised planets, has a diameter of 4.88 times 10 to the 6 metres and a mean density of 5.4 times 10 to the 3 kilograms per metre cubed. Calculate the gravitational field at its surface. Then a man has a weight of 700 newtons on the Earth's surface. What would his weight be on the surface of Mercury? So pause the video now, then unpause the video when you want to go through your answer. Right, so for this first one again, you're going to have arrows directed towards the Earth because the gravitational field goes in the direction that a point mass would move in. Gravity is always attractive, so it points towards the centre of the planet. Now you can't use the equation E equals mg delta h because for a rise of 10,000 metres, g, the Earth's gravitational field strength, can be considered to be uniform, so we can use that equation, but for a greater change in distance, g will change, so therefore that equation it cannot be used because g is no longer constant. Now, how can we work through the gravitational field? Well, we know that the mass of Mercury is going to be equal to density times by volume. We know the volume is going to be 4 over 3 pi r cubed because it's a sphere. So we can work out the mass by it'd be 3.286 times 10 to the 23 kilograms. We know G equals big G big M over r squared. We've just worked out M, so therefore we can work it through to be 3.7 newtons per kilogram. Now the next question is, what would the weight be on the surface of Mercury? Well, we've just worked out what small g would be, 3.7 newtons per kilogram. So weight is mass times by gravity, so it's 700 times by 3.68, so it's 340 newtons. The next question says, what is the gravitational potential and what are its units? What is the significance of the negative sign in the gravitational potential equation? Sketch a graph of gravitational potential against distance for an object in the Earth's gravitational field. What does the gradient of a graph of V against R tell you? And find the gravitational potential at the surface of the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, so definition of gravitational potential is it is the gravitational potential energy that a unit mass would have at that point in the gravitational field, and it's measured in joules per kilogram. The significance of the negative sign is that because gravitational fields are inherently attractive, so therefore we say that at infinity, or when you're out of the field, that the gravitational potential is 0. Now you've got to put energy in to get out of that attractive field. So if you put an energy in to get to 0, well therefore it must start off at a negative value because work is having to be done to move it out of the field. So the gravitational potential against distance graph would look something like the following. It's proportional to 1 over r, and it's in a negative, so it'll go through as a curve like so. Now the gradient of V against R, well we know V against R is going to be Gm over R again, so it's going to be Gm over R squared, which we know is the gravitational field strength. So therefore the gradient will be the negative G at that point. And then to work out this gravitational potential, well it's minus Gm over R. Pop in all the values. We've got the radius of the Earth given to us on the equation sheet. We can pop it through to be minus 6.26 times 10 to the 7 joules per kilogram. The next question says, state in words Newton's law of gravitation. By considering the centripetal force which acts on a planet in circular motion, show that t squared is directly proportional to r cubed, where t is the time taken for one orbit around the sun and r is the radius of the orbit. Now the Earth's orbit is of a mean radius 1.50 times 10 to the 11 meters, and the Earth's year is 365 days long. The mean radius of the orbit of Mercury is 5.79 times 10 to the 10 meters. Calculate the length of Mercury's year. Then Neptune orbits the Sun once every 165 Earth years. Calculate the distance from the Sun to Neptune divided by the distance from the Earth to Neptune. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this particular question, you've got to know what the Newton's law of gravitation is. That gravitation is going to be attractive between point masses. The force of the attraction is going to be proportional to the product of the two masses, but inversely proportional to the square of the separation of those two masses. Now in this next question, we know we can link that the centripetal force in this context is the gravitational force of attraction. So the general equation for the gravitational force force is gmm over r squared, and the general equation for centripetal force is m omega squared r. And we know T is going to be equal to 2 pi over omega, so therefore omega we can then link into is going to be 2 pi over T. We can pop all those values into that equation, and then we can substitute that down. So we can say 4 pi squared over T squared equals gm over r cubed. We know that 4 pi squared, and we know that gm in these contexts are constant, so therefore tells us that proportionally T squared is directly proportional to r cubed. Now we can therefore use that to work out the length of the year. So if we know T squared is directly proportional to r cubed, well, we can say that T squared of Earth over T squared of Mercury T squared of Earth over r cubed of the Earth equals T squared of Mercury over r cubed of Mercury. Now we know throughout the four of them, we know the time of the Earth year, we know the distance between the Earth and the Sun, we know the distance between the Earth and between Mercury and the Sun. Now you don't have to convert the time into seconds because it's a ratio, so it would work out a value in days, so it's 87.5 days. Now again, we can use this ratio idea to work out the distance between the Earth and Neptune ratio to the distance between Neptune and the Sun. So we can say that the T squared for the Earth over r cubed for the Earth is equal to T squared for Neptune over r cubed for Neptune. Now we just need to work out r cubed for Neptune, so we can work that out by popping in all the values. Remember that the Earth's orbital time period is 1 Earth year. Again, we don't need to change the units for time because it's a ratio. So we work out that the radius of Neptune to the Sun is 4.51 times 10 to the 12 meters. So we can therefore work out that the ratio between the two of them is equal to 30. The next question says, a student believes it's possible for a satellite to be in a geostationary orbit above London. Firstly, explain why a satellite could not be in a geostationary orbit above London. Then the height of a geostationary orbit is 36 times 10 to the 6 meters. Show that the speed of a satellite in a geostationary orbit is about 3 kilometers per second. And then calculate the total energy in joules of a geostationary satellite of mass 282 kilograms in this orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, why can't it be in a geostationary orbit above London? Well, to remain in orbit, there must be a force perpendicular to the direction of motion. Now, this satellite could not maintain this orbit without an engine or other force or engine input. Now, you can only really maintain a geostationary orbit when you're in a plane above the equator. Now, in the next one, we can work out what r is going to be, because it's the distance from the surface to the object plus the radius of the planet, which we are given on the equation sheet. We can then work out what the time is going to be by working out the time for by 24 times by 60 times by 60. That is going to be the number of seconds in one day. And then we'll say v is equal to the distance, which is going to be 2 pi r from the ideal to circular orbit, divided by the time, so we get 3081 meters per second, or 3 kilometers per second as well. Now, how can we work out our total energy? Well, we know that the total energy for an orbit is the kinetic energy plus the potential energy store. We know that the kinetic energy is a half mv squared, but in this context it's going to be gmm over 2r when we work it through. We know that the potential is going to be equal to negative gmm over r, because we can't use mgh, so therefore we can work through our value to be minus gmm over 2r. Pop in all the numbers. We know r is the distance from the center of mass, not the distance from the surface. We can pop in all the numbers and we work it out to be minus 1.3 times 10 to the 9 joules. The next question says, define the gravitational field strength, and then the table shows in modern units information that was known to physicists at the time of Isaac Newton. Firstly, state the relationship between the gravitational field strength g and the distance r and verify this relationship. Show that the mass of the Earth is about 6 times 10 to the 24 kilograms and determine the mean density of the Earth. So pause the video now, then unpause the video when you want to go through your answer. Right, so the gravitational field strength we know is the force per unit mass at a point in a gravitational field. That's a definition you've just got to be able to recall. Now, how can you verify a relationship? Well, we know that the relationship should be g is directly proportional to 1 over r squared. So we can therefore say g is equal to k over r squared, where k is just the proportionality constant. Now, if it's a verified relationship, that proportionality constant should be the same for each particular object that you know. know, so therefore K will be equal to G R squared. So you do G R squared for each of the values. Now you don't have to convert units because we're just looking for a same value at this point. So as long as it's in the same units, it should be fine. So you work it through. They are roughly the same number. One is 4 times 10 to the 8. The other is 3.9 times 10 to the 8. So therefore they're close enough to be correct. Now for the next question, where we're looking at the mass of the Earth, well, we know that G is going to be equal to gm over r squared, so therefore we can work through that it's going to be m is equal to gr squared over g. So we can say it's going to be 9.81 times by 6.4 times 10 to the 6 squared over 6.67 times 10 to the minus 11, so it's 6.024 times 10 to the 24 kilograms. Then we can work out the mean density, because density is going to be mass over volume. The Earth is a sphere, so it's 4 over 3 pi r cubed, so you can work it through that way, and then you pop in the mass you've just calculated before divided by the volume, which is worked out by 4 over 3 pi r cubed, so you get 5,500 kilograms per meter cubed. Now the next question says, state the name given to the satellites that orbit the Earth with a period of 1 day above the equator. Explain why these satellites orbit above the equator. Then for companies who provide a satellite TV service, suggest the main advantage of using this type of satellite. Now the mass of the Earth is 6 times 10 to the 24 kilograms. Show that the radius of the orbit of a satellite with an orbital period of 1 day is about 4 times 10 to the 7 meters, and then state Kepler's third law. And then the moon orbits the Earth with a period of 27.3 days. Use the information to calculate the ratio of the distance of the moon from the Earth's center divided by the distance of the satellite from the Earth's center. So pause the video now, then unpause the video when you want to go through your answer. Right, so this is just a fact. We know that it's a geostationary orbit or a synchronous orbit. That's just a fact you've got to learn. Now they have to be above the equator, so they can stay at the same point at all times above that part of the Earth, which can only take place if it's at the equator, because that's the point which will stay stationary to that rotation when you're doing 1 day. Now again, the advantage of using geostationary orbits is that the dish can be fixed to just one point in the sky, because it's always at that point, so the dish doesn't have to track the satellite as it moves across the sky from the perspective of the Earth, so it's easier for them to sort that out. Now the next one, we're using this equation of t squared is equal to 4 pi squared over gm r cubed. So therefore you can make r cubed the subject, pop in all the values, and remember you can work it through to get r out, which is 4.2 times 10 to the 7 meters. Now in the next question, how can we work out what's Kepler's third law? Well, it's that t squared is directly proportional to r cubed, so the cube of a planet's distance from the sun divided by the square of the orbital time period is the same. It's a constant, and we can use that idea of that ratio, that that r cubed is equal to t squared or proportional to t squared, by looking it through. Now again, we know the time it takes for the Earth to orbit the moon to orbit the Earth. We know it's 27.3 days. We can then work out how long it takes for the Earth to orbit again, to go around itself once, which is 1 day. So therefore we can go 27.3 over 1. Okay, that's all squared, so you can work through that ratio to be 9.1. The next question says, planets outside our solar system are called exoplanets. An exoplanet of mass 5.69 times 10 to the 27 kilograms orbits a star of mass 3.83 times 10 to the 30 kilograms. Compare the mass of the star with the mass of the exoplanet in terms of orders of magnitude, and then the distance between the exoplanet and the star is 3.14 times 10 to the 11 meters. Calculate the gravitational force between the star and the exoplanet. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what you've got to do is you've just got to divide the two masses by each other. So it's 3.38 times 10 to the 30 over 5.69 times 10 to the 27. So that equals 673. So therefore you can say it's about 3 orders of magnitude greater when you work it through. So therefore you can say that's about 3 orders, because it's going to be about 10 to the 3. So 10 to the 30 divided by 10 to the 27 is going to be 10 to the 3. So it's 3 orders of magnitude greater. We can then use our equation for the Newton's law of gravitational attraction to put in all the values. Remember, it's r squared, so we get F is equal to 1.47 times 10 to the 25 newtons. The next question says, a space vehicle has a mass of 16,800 kilograms as in an orbit 900 kilometers above the surface of the Earth. Then we give the mass of the Earth, the radius of the Earth, so show the orbital speed of a vehicle is approximately 7,400 meters per second. Now the space vehicle moves from the orbit of 900 kilometers above the Earth's surface to an orbit 400 kilometers above the Earth's surface, where the orbital speed is 7,700 meters per second. Calculate the total change that occurs in the energy of the space vehicle. Assume that the vehicle remains outside the atmosphere after the change of orbit and use the value of 7,400 meters per second for the speed in the initial orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we've got to say that the gravitational force of attraction is equal to the centripetal mass, so therefore we can work that then through to work out what v is. The orbital speed is going to be square root of gm over r, so as a result we can pop in all the values. Now again, remember, r is from the centre of the planet to the objects. We add the radius of the planet in there, so we get it out to be 5.4 times 10 to the 7 meters per second, sorry, 5.4 times 10 to the 7, so therefore square rooted is 7,396 meters per second. Now again, in this next one, we know that potential energy is gmm over r, and we also kinetic energy in this case is a half mv squared, so we can work out the change in potential by doing it at 900 kilometers and doing it at 400 kilometers. But again, remember, we've got to work from the center of mass of the Earth to the actual object, so we've got to work it through from the actual center of mass of the object, and that can work out that the potential energy is equal to minus 6.8 times 10 to the 10 joules. Now we then know kinetic energy is a half mv squared. Now we can work it through in terms of what the speed was at the start compared to the speeds at the end by doing your v squared like so. So we get our change in kinetic to be 3.81 times 10 to the 10 joules. We then subtract one from the other to find the change, so therefore we get minus 2.99 times 10 to the 10 joules. The next question says, the NASA space probe Dawn has travelled to and orbited large asteroids in the solar system. Dawn has a mass of 1,240 kilograms. The table gives information about two large asteroids orbited by Dawn. Both asteroids can be considered to be spherical and remote from other large objects. Dawn began orbiting Vesta in a circular orbit at a height of 680 kilometers above the surface of the asteroid. The gravitational force acting on Dawn at this altitude was 24.1 newtons, so that the tangential velocity of Dawn in this orbit is 135 meters per second. Calculate the orbital period of Dawn. Then later in its mission, Dawn entered the orbit around Ceres. It then moved from a high orbit to a lower orbit around the asteroid. State what is meant by the gravitational potential of a point in space. Then Dawn has a gravitational potential of minus 1.29 times 10 to the 4 joules per kilogram in the high orbit, and then a gravitational potential of minus 3.22 times 10 to the 4 joules per kilogram in the lower orbit. Determine the change in potential energy of Dawn as a result of this change in orbit. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we can then work out what the value of the tangential velocity is going to be, because you know it's a circular orbit, so therefore it's a centripetal force acting on the object. So F equals mv squared over r. We've got all the values except for v. Remember, r is from the center of mass of the planet, so we've got to include the radius of the planet in that. So r works through to be 135 meters per second. The orbital period is going to be v equals to be distance over time, which is 2 pi r over t. Again, we've got r, we know 2 pi, we've just worked out v to be 135, so therefore t equals 4.39 times 10 to the 4 seconds. Gravitational potential we know is the work done in moving a unit mass from infinity to that point in the gravitational field. That's a fact you've just got to remember. And then the change in potential energy is going to be equal to, when you're working it through, the change in potential, which you can work out to be minus 1.93 times 10 to the 4. Then the work done is the mass times by this change in potential. You've got the mass of the thing that's moving, which is Dawn in this case. So it's minus 2.39 times 10 to the 7 joules. The next question said Galileo was the first person to observe Jupiter's larger moons. Ganymede is Jupiter's largest moon. The distance between the centre of Ganymede and the centre of Jupiter is 1.07 times 10 to the 6 kilometres. Ganymede takes 171 hours to complete an orbit around Jupiter. Calculate the mass of Jupiter. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work this through? Well, the first thing is you can work out what the orbital time is by doing 171 times by 60 times by 60, so it's 615,600 seconds. We can then use the idea of the centripetal force is equal to the gravitational force of attraction to then get out an equation for gm equals 4 pi squared r cubed over t squared. That's Kepler's law of orbits. So therefore we can rearrange that and make m the subject, pop in all the values that we've got, so we get 1.91 times 10 to the 27 kilograms. The next question says Makey is a dwarf planet in the solar system. Makey has a mass of 3.1 times 10 to the 21 kilograms and a radius of 715 kilometers. Calculate the gravitational field strength at the surface of Makey, and then the distance of Makey from the sun is similar to the average distance of the dwarf planet Pluto from the sun. A website states the time taken by Makey to complete one orbit of the sun is 20% greater than the time taken by Pluto to complete one orbit of the sun. Assess the accuracy of the website statement. So pause the video now, then unpause the video when you want to go through your answer. Right, so this first one, gravitational field strength, how do you work that through? It's gm over r squared. Pop in all the numbers, you've got the values given to you. Remember, we don't work in kilometers, we work in meters. Remember to square the value for r and we get 0.404 newtons per kilogram. Now the next question, we can work out what the angular speed is going to be by doing angular speed is equal to the square root of gm over r cubed, and we can work that through to be 6.5 times 10 to the minus 10 radians per second. We can then work out therefore the orbital time by doing t equals 2 pi over omega, and therefore we can work it out to be 9.67 times 10 to the 9 seconds, which is 307 years. So now we've got the time period for Makey, and we already had the time period for Pluto, both in years, because we're going to ratio them, it doesn't make a difference. So therefore we can ratio the two of them. 307 divided by 248 is 1.24. So the orbital time of Makey isn't actually 20% greater, it's 24% greater than that of Pluto. So it's not as accurate as we would like it to be. So that brings an end to our revision session today. So hopefully if you've been successful and you've learned in this revision session, you should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and understand what topics you need to improve upon for A-Level Physics for the gravitational fields topic. So thank you very much for participating in this revision session for gravitational fields for the AQA Physics exam board on paper 2 and on this particular gravitational fields topic. Thanks so much and have a lovely day. Hello and welcome to this revision session on gravitational fields, which is part of the AQA A-Level Physics qualification. So in this revision session we're going to look at how you can answer questions on gravitational fields. So how should you prepare for this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the section on the right hand side. In this left hand section, write down your working out or answers to the questions in the revision session. Now when you're doing this, make sure to write in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions you gained from this revision session. Now after the end of this revision session, write up these notes into a revision sheet for you to use independently. So what are some tips on revision? Well, you should be independently revising physics in 3 steps. The first step is to learn the key facts. So use your revision guide, your class workbooks, your preparation notes and the textbook to learn the key ideas of the course. Learn the knowledge and the facts that you need to know for AQA A-Level Physics. And you can do this by writing out mind maps or writing out the notes yourself. The second step is to then test yourself. So use like the Caboodle e-learning platform, the Seneca e-learning platform, and Knowledge Checker to quickly test your own knowledge on the key facts of the course. Now you may wish to do this by making and using your own cue cards. Then this third step is then to practice examination questions. So use examination prep books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work. Now you may wish to download your own examination papers to do this. So these 3 steps of learning the key facts, testing yourself, and then practice examination questions are the way in which you can prepare for an AQA A-Level Physics examination. So let's now have a look at step 3, practicing some examination questions. So let's look at the following question. Part 1. Define the gravitational potential at a point in a gravitational field. Figure 5, which is not drawn to scale, shows the region between the Earth and the Moon. Now the gravitational potential at the Earth's surface is minus 62.6 megajoules per kilogram. Point X shown on figure 5 is in the line of the centres between the Earth and the Moon. At X the resultant gravitational field is 0 and the gravitational potential is minus 1.3 megajoules per kilogram. So calculate the minimum amount of energy that we require to move a moon probe of mass 1.2 times 10 to the 4 kilograms from the surface of the Earth to point X, and express your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through the answer. Right, so the first one is a key definition you just need to learn. You've got to learn your key definitions of fields, which includes potential, field strength, potential difference. So, the gravitational potential is the work done or energy required per unit mass. Remember, you've got to say per unit mass for anything in a gravitational field in moving a mass from infinity to a point inside the field. Now remember, just the energy per unit mass is the absolute gravitational potential, but the gravitational potential is always defined as the energy per mass, or the work done per mass, in moving from infinity, which is going to be where the value is 0, into the gravitational field. Now in this next question, what can you surmise and work out? Well, you know firstly that the gravitational potential is at X is minus 1.3. Now you'll notice that at the surface it's minus 62.6. So therefore the first thing you can do is work out the potential difference. So the potential difference in moving from the Earth to the point X is going to be 61.3 megajoules per kilogram. Now you should then also remember that if we have a potential difference and we need to work out an energy or a work done, well therefore work done is mass times by potential difference. Now you're given the mass in the question of the moon probe, it's 1.2 times 10 to the 4, so you'll do 1.2 times 10 to the 4 times by 61.3 times 10 to the 6. Remember, your megajoules will turn into times 10 to the 6. Then you get your answer of 7.4 times 10 to the 11 joules. Now again, remember, it asks you to write it to the appropriate number of significant figures. Now you'll notice that there is 3 in 62.6, 2 in 1.3 and 2 in 1.2 times 10 to the 4 in the values given in the question, and you always go to the lowest number of significant figures, so you'd write it to 2 significant figures only. Next question. Explain why, once the probe is beyond X, no further energy would have to be supplied in order for it to reach the surface of the moon. And then in the vicinity of the Earth's orbit, the gravitational potential due to the sun's mass is minus 885 megajoules per kilogram. With reference to the variation in gravitational potential with difference, explain why the gravitational potential due to the sun's mass need not be considered when you carried out your previous calculation. So pause the video now, then unpause the video when you want to go through your answer. Now you'll notice in these two questions that there's no calculations required, rather it's just your understanding of fields and what we actually are working out with these terms of potential, with potential difference and field strength, so whichever. Now you'll notice, okay, that beyond X the gravitational potential decreases as the moon is approached, because now the gravitational field of the moon will attract the probe towards it. It's always important to remember that any gravitational field will cause an attractive force to be acting on the object in the field, wanting it to pull it to the center of mass of that gravitational field. Remember, gravitational fields always produce attractive forces. Now in the second question, you've got to now consider why the potential of the sun will not be considered. Now again, it's saying the variation in gravitational potential with distance. So the first thing you've got to be aware of is quite clearly the distance from the Earth to the sun is much larger than the distance of the Earth to the moon. So therefore the change in potential over the Earth to the moon distance from the sun is negligible, so it's not changed a great amount when doing this, so it does not need to be considered. Next question. The amount of energy required to move a manned spacecraft from the Earth to the Moon is much greater than that's required to return it to the Earth. By reference to the forces involved, to gravitational field strength and gravitational potential, and to the point X, explain why this is so. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to consider all the following ideas. You've got to consider the gravitational forces involved, the gravitational field strength involved, and the gravitational potential. So I would, in this question, segment it into three key areas. So let's have a look at them. So for gravitational forces, that the spacecraft experiences gravitational attractions to both the Earth and the Moon during its journey, because it'll be in both their gravitational fields, so it'll be attracted towards each of them. Now these forces pull in the opposite directions on the spacecraft, because one's pulling towards the Earth, one's pulling towards the Moon. Now because the Earth is much more massive than the Moon, then for most of the outwards journey the overall resultant force is towards the Earth as opposed towards the Moon, but only in the latter stage of the outward journey is that resultant force towards the Moon, because you're much closer to the Moon at that point. Now on the return journey the resultant force is predominantly towards the Earth, because that is going to be producing that larger gravitational force. Now in terms of gravitational field strength, as you're leaving the Earth's gravitational field, and it's a radial field, the Earth's gravitational field becomes weaker and the Moon's becomes stronger, because you're going towards the Moon, so you're going into that radial field but out of the Earth's radial field. Now the resultant field strength is always going to be the vector sum of the Earth and the Moon's gravitational field strength acting on this particular probe. Now at point X it did say that the gravitational field strength was 0, so that indicates that the gravitational field strength from the Earth and the gravitational field strength from the Moon at that point is going to balance out and going to be 0. Now X is much closer to the Moon than it is to the Earth. Why is that? Because the Moon is much less massive than the Earth, so its gravitational field strength is going to be a lot smaller in the equivalent distance than the Earth's would be. Now once X has been passed, if the spacecraft will want to be attracted towards the Moon, because the gravitational field of the Moon is then more dominant, but on the return journey the spacecraft will go towards the Earth once it's beyond that point X. Now finally, gravitational potential. Now the gravitational potential due to the Earth increases, so becomes less negative as the spacecraft moves away from the Earth. Now the resultant gravitational potential again is the sum of those due to the Earth and the Moon separately, but remember, because gravitational potential is an energy, it's a scalar, not a vector like gravitational field strength. Now at point X the gravitational potential reaches a maximum value before decreasing as the Moon is approached, because again it'll be attracted towards the Moon, so therefore it will lose value as it goes closer to the Moon. So in order to reach M on the outward journey, the Moon, the spacecraft has to be given at least enough energy to reach X, and the vice versa for the return. Now much more work is needed to move the spacecraft from the Earth to point X, because it's a much further distance away, so therefore it's going to be a larger force overcome. So then it will be from the Moon to X, because the Moon is producing a smaller gravitational field because it's got less mass, so you need less force to then overcome that to then reach point X, then be encountered with the Earth's gravitational field and be attracted towards it. Next question. Figure 1 shows the orbits of two Earth satellites, a communication satellite in a geosynchronous orbit and a monitoring satellite in a low orbit that passes over the poles. The time period t of any satellite in a circular orbit around a planet is proportional to r to the power of 3/2, where r is the radius of the orbit measured from the centre of the planet. For a satellite in a low orbit that passes over the poles of the Earth, t is 105 minutes, where r is 7,370 kilometres. So this question asks us to calculate the height above the surface of the Earth in kilometres of a satellite in a geosynchronous circular orbit, and again give your answers to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's important to note the following, because you're going to be looking at the idea of what the value of r is going to be, the height above the surface of the Earth. So what you would want to do is want to work out the value of r for the satellite and then subtract the radius of the Earth from that answer, because you're trying to work out the height above the surface, and the value of r you're going to calculate is going to be from the center of the planet to the actual satellite. So what you would say is as follows. You can say that t is directly proportional to r to the power of 3 over 2, or you could say t squared is directly proportional to r cubed, same thing. So what you can therefore say is that you can ratio the two. So you can say that TE, time period of the Earth, divided by TP, time period of the probe, is equal to RE, the radius of the Earth, divided by RP, the radius of the probe's orbit, all to the power of 3 over 2. Now, the important thing to note is, okay, do you have to convert the values? Now, the first instinct is you're saying, oh, it's kilometers, it's meters, and we're doing physics and we tend to work in meters and seconds, we need to convert the actual units. Well, you could if you wanted to, but because we're ratioing the two values, you don't actually need to do this. So you pop in the numbers, but what you've got to remember is, well, what's the time period of the Earth's orbit? So you would do, well, in one orbit it's going to be 24 hours, well, rotation, sorry. So one rotation will be 24 hours, but we're working in minutes because the other value is given in minutes. So you convert the time period of the Earth's rotation to be 60 times by 24 to get into minutes, divided by the time period of the probe, 105 minutes, as given in the question, is equal to RE divided by 7,370, which is going to be your value of your probe. As you can see in the previous question, it tells you what the value of r to the probe is going to be. So at that point, we can therefore work out what our value is going to therefore work through, and we get our answer to be 42,200 kilometers. Then you subtract the radius of the Earth from that, because we're going from the height of the surface, not from the center of the planet, and therefore you get your answer to be 35,800 or 35,900 kilometers. Why give it to three significant figures? Well, you'll notice in the question 105 is three significant figures, 7,370 is either 3 or 4 significant figures. You always go with the lowest number of significant figures in an answer, so it will be 3 significant figures. Another way you could do it is you could also use Newton's law of gravitation, as you can see on the screen at the minute. So you could say, well, F is equal to G big M small m over r squared, and r squared is what r is what we want to work out. So therefore you can work it through, but you can also say that because it's the gravitational force is causing circular motion, well, therefore you can equate it to the centripetal equation of m omega squared r, and therefore omega is 2 pi over t. You can work it all through, put the numbers in, work out your answer, and once again get 42,200 kilometers, which then you subtract the radius of the Earth from that, because we're measuring from the surface of the Earth, not the center of mass. Next question. These geosynchronous and polar satellites have different applications because of their different orbits in relation to the rotation of the Earth. Compare the principal features of the geosynchronous and polar orbits and explain the consequences for the possible uses of satellites in these orbits. In your answer, you should explain why a low polar orbit is suitable for a satellite used to monitor conditions on the Earth, and a geosynchronous circular orbit above the equator is especially suitable for a satellite used in communications. So pause your video now, then unpause the video when you want to go through your answer. So it's very important that you read these types of questions and make sure you answer every bullet point in the question. So the first thing you would want to do is talk about all of the facts about low polar orbits in one paragraph, and then in the second paragraph talk about all the facts about geosynchronous orbits above the equator and compare and contrast the two. So therefore it's really important you learn your key facts and your key ideas about both types of orbits. So a low polar orbit has an orbital period of a few hours. Now the Earth rotates relative to the orbits, they're not synchronous as the name suggests. Now many orbits with different radii and different periods are possible because you're just looking to go over the poles, so therefore you can have different possible trajectories in your paths. Now the orbit height is a lot less than that of a geosynchronous orbit. Now again, if you really want to get full marks in this type of question, you need to compare them. So literally saying it's less will give you more marks there than just saying it's got a small value for the height. The next one is that the speed is greater than that of a geosynchronous orbit. That occurs because it's got a lower orbital height. satellite. Now, what's some applications of the low polar orbits? Well, because the satellite can easily scan the whole surface of the Earth, applications can include surveillance of conditions or installations on the Earth, like Google Maps, for example. You can have weather observations, or you could have environmental monitoring. So the important thing to note about low polar orbits is that it gives access to every point on the Earth's surface every day, and it can allow you to collect data from regions inaccessible to humans normally. But the issue you would have is the contact with the transmitting and receiving area is intermittent because it's continually moving its position relative to the Earth. So you would need to have a tracking facility involved, but the positive would be you would need a lower signal strength than that of a geosynchronous orbit because it's closer to the surface of the Earth. Now, what do you know about a geosynchronous orbit above the equator? Well, the orbital period will match the Earth's rotational period exactly, so the satellite will maintain the same position relative to the Earth, so it's always above the same point on the Earth's surface. So therefore only one particular orbital radius is possible, that of the equator. Now it travels to west to east above the equator because it has to rotate, has to move in the same direction as the Earth's rotation. Now the orbital height of a geosynchronous satellite, to maintain this, has to be higher than a polar orbital satellite, so therefore its speed will be lower because it's further away from the surface of the Earth, and its scans are only restricted to one particular area on the Earth's surface, so you would tend to use it for telecommunications, satellite TV, radio, in digital transmission. Now the satellite would therefore be in continuous contact with the transmitting and receiving aerial, so therefore going to be in a fixed position because it's always in the same position above the surface of the Earth. So it's important that you can compare and contrast the two orbits, so you need to learn your key facts about each one. Now, next question. Define gravitational field strength and state whether it's a scalar or a vector quantity. And then a mass m is at a height h above the surface of a planet of mass m and radius r. The gravitational field strength at height h is g. By considering the gravitational force acting on mass m, derive an equation from Newton's law of gravitation to express g in terms of big M, big R, h, and the gravitational constant big G. So pause the video now, then unpause the video when you want to go through your answers. Right, so again, you've got to learn your key definition of fields. So gravitational field strength, just learn it, it's a fact. It's the force per unit mass experienced by an object inside a gravitational field. Now, it's got a force there, which is a vector, so the quantity will be a vector. Now the next question is you've got to be able to equate your equations and work them through. So if we know that the force on the body of a mass is given by the following equation. Well, we know from Newton's law of gravitation, force is equal to big G, big M times by M over R squared. But remember, this R squared is the separation from the object, the mass, and the center of mass of the object producing the field, which in this case is the planet. So it's going to be big R, which is the radius of the planet, plus h, the distance from the surface of the planet to the actual orbiting body. So we'd say it's actually big R plus h all squared. Now we know gravitational field strength is therefore going to be force over mass, because gravitational field strength is force per unit mass. So therefore we can equate that by taking our equation for force we've just written out and dividing it all by mass. So what that basically means is that small m, the mass of the object itself, cancels through, and you get your equation of big G, big M over big R plus h all squared. Next question. A satellite of mass 2,520 kilograms is at a height of 1.39 times 10 to the 7 meters above the surface of the Earth. Calculate the gravitational force of the Earth attracting the satellite and give your answer to the appropriate number of significant figures. So pause your video now, then unpause the video when you want to go through your answers. So you've just got to use the equation we had before. So we know before that F is equal to big G, big M, small m over R plus h all squared. Now again, remember, we don't need gravitational field strength, which we worked out by dividing that equation by m. We're looking for the gravitational force, which is given by Newton's law of gravitational attraction. So we pop all our numbers in. Now remember, it's the Earth. Now we get the mass of the Earth from the equation sheet. It's 5.98 times 10 to 24. You're given the mass of the satellite, and you should be able to get the gravitational constant from, again, the equation sheet of 6.67 times 10 to minus 11. You then divide that value by the distance from the centre of mass of the planet to the actual object. Now again, remember that we were given the radius of the planet in kilometres, so convert that into metres, work it through, and you get 2.45 times 10 to the 3 newtons. Now again, why 3 significant figures? Well, 1.39 is 3 sig fig, 2,520 is either 3 or 4 sig figs, but we always go with the lower number, so we have to give it to 3 significant figures. Let's now look at the following question. The satellite in that previous question is in a circular polar orbit. Show that the satellite will travel around the Earth 3 times every 24 hours. Then state and explain one possible use for the satellite travelling in that orbit. So pause the video now, then unpause the video when you want to go through your answers. Right, so in this first question, it's 5 marks, so we're going to have to do quite a bit of derivation. So the first thing we need to do is we've worked out a value of force, so we can say that F is equal, okay, to m omega squared times by r. Now in this case, r is the distance from the centre of mass of the planet to the actual position of the satellite. So we're going to as big R, which is the radius of the planet, plus h, the distance from the surface to the actual object. So you can work out omega by doing that and working it through, so you get your answer to be 2.19 times 10 to the minus 4 radians per second. We then know that time period is therefore equal to 2 pi over omega, because omega is equal to 2 pi over time period. So therefore it's 2 pi over the previous value we've worked through, which is 2.87 times 10 to the 4 seconds. Therefore it shows that if we know how many seconds are in a day, we can then work out that there are approximately 3 transits. So you'd work out how many seconds there are in a day, divided by the number of 2.87 times 10 to the 4, and you see there's approximately 3. The other way you can do that is you can also do it by looking at the equation F is equal to mv squared over r, which then gives us v by working it through, so you get it to be 4.4 times 10 to the 3. Therefore you can say time period is going to be equal to 2 times by pi times by the diameter, by the radius, so 2 pi times by the radius over the velocity, because we're saying that basically time is going to be equal to the distance it travels, the circumference of the orbit, divided by its velocity, which we just worked out. So you get 2.87 times 10 to the 4 seconds. Then once again show that it's approximately 3 transits in one day by working out how many seconds there are in a day, divided by that value, and you'll see the number is approximately 3. Now again, how to answer these types of questions is always remember that an object carrying out a circular orbit is carrying out circular motion. So all the equations we looked at previously for circular motion, such as F equals mv squared over r, and F equals m omega squared r, and omega equals 2 pi over t, are still applicable in this situation. Now the next question is asking what could we use a satellite which has basically, if you notice, a circular polar orbit, what could it be used for? Well, it can be used for anything which is such as monitoring weather or surveillance or GPS or communications. But remember, you've got to say as communications, the issue is it's intermittent contact, because it's not always over the same point on the Earth's surface. Or if you're going to use GPS, you would say you need to have several satellites in a network to continually be scanning over the Earth at all times. Next question. The planet Venus may be considered to be a sphere of uniform density of 5.24 times 10 to the 3 kilograms per meter cubed. The gravitational field strength at the surface of Venus is 8.87 newtons per kilogram. Show that the gravitational field strength G at the surface of the planet is related to the density and the radius of the planet by the expression G is equal to 4 over 3 pi big G times big R times by density. Now then finally calculate the radius of Venus and give your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you work this one out? Well, the first trick for me is you're given the fact that you're given density and you've got 4 over 3 pi. So it's going to be involved in the equation that density is equal to mass over volume, because you know volume of a sphere is 4 over 3 pi r cubed. So therefore you would say the first thing is that mass equals density times by volume, so therefore it's the volume, which is 4 over 3 pi r cubed, times by the density. We therefore also know that gravitational field strength is big G big M over r squared, so therefore you can pop it in because you can sub in that value for M into that gravitational field strength equation, cancel it through and get that equation out. Next one, how do you then calculate the radius of Venus? Well, you take this equation which you've just worked out, which has been given or you've just worked out, and you make r the subject. So you say that r is the subject, so it'll be 3g over 4 pi big G rho. You can then work it all through because you've been given small g in the question, you've been given rho in the question, you know what big G is, you know what 4 pi and 3 are, so you can work it out to be 6.06 times 10 to the 6 meters, and you give it to three significant figures. Why is that? Well, in the question you got 4.24, 8.87. They are both three significant figures, so your answer is given to three significant figures. Next question. At a certain time, the positions of Earth and Venus are aligned so that the distance between them is a minimum. Sketch a graph on the axis below to show how the magnitude of the gravitational field strength G varies with distance along the short straight line between their surfaces. Consider only the contributions to the field produced by Earth and Venus and mark values on the vertical axis of your graph. So pause the video now, then unpause the video when you want to go through your answer. Well, once again, it's very important you can graphically represent the properties of gravitational fields. Now, it's gravitational field strength, and you should know for radial fields, it follows the inverse square law, so it should be a curve going down. Now, the first thing to note is, well, what's it going to start off at the surface of the Earth? Well, it's a fact, and you should hopefully remember from GCSE, that the gravitational field strength at the surface of the Earth is going to be 9.81. Now, you know that the field strength of Venus is 8.87. Now you know that because I told you in the question previously, and they'll follow the inverse square law, so you'll see that curve and that curve and graph being drawn, and you notice there'll be a point which is exactly 0 when the two gravitational fields cancel out. So that's the sweet spot where you would have actually no overall gravitational field strength. Let's have a look at the next question then. So the first one is define the gravitational potential at a point, then explain why gravitational potential is always a negative, then show that the magnitude of the gravitational potential of the Earth's surface due to the mass of the Earth is about 6.3 times 10 to the 7 joules per kilogram. Then a satellite is launched into a geostationary orbit. Describe and explain two features of a geostationary orbit. So pause the video now, then unpause the video when you want to go through your answers. Well, once again, you'll see that there's just key facts about fields you've got to learn. So once again, what's the definition of gravitational potential? It's the work done per unit mass in moving from infinity to a point inside the field. Always remember your key definitions. Now, another bit of the gravitational field which always comes up on exams is explaining why potential is always a negative, and that's due to the fact that gravity is an attractive force. So we define that at infinity, at outside the field, the potential is 0. Now, if you are putting work in to get an object to 0 out of the field and to infinity, well, therefore the value must start as a negative number. Next one is then use your equation to work out the value of the gravitational potential. Now, notice it says the magnitude of gravitational potential. So whilst the equation is V is equal to minus gm over r squared, you can ignore the minus because it's asking for the magnitude. So you would pop in the value of the universal gravitational constant. The mass of the Earth, which you know is given in the equation book, is 5.97 times 10 to the 24 kilograms. And then we know our distance, because again you're given the radius of the Earth in your examination book, is 6.37 times 10 to the 6 meters. Pop it all through and you get 6.25 times 10 to the 7 joules per kilogram. Now the next thing again is explaining what a geostationary orbit is. So the first thing you've got to always say is it's in the plane of the equator, it's always fixed above the same location on the Earth, and it will always have the same period as the Earth, which is 24 hours, and it will rotate in the same direction as the Earth rotates itself. It's very, very important that you can state your facts about a geosynchronous orbit. Let's have a look at the next question. The satellite has a mass of 1,200 kilograms and the radius of its orbit is 4.23 times 10 to the 7 meters. Calculate the gain in gravitational potential energy of the satellite when it's placed into orbit from the Earth's surface, and then impulse engines are used to place the satellite into an orbit with a longer period. Discuss any changes this makes to the orbital motion of the satellite. So pause the video now, then unpause the video when you want to go through your answer. So, how would you answer this type of question? Well, you've got to think about the gain in gravitational potential energy. Now, don't be tricked and think you've got to do the equation E is equal to mg delta H like you would do with GCSE. The reason why we can't use this equation is because the value of G, the gravitational field strength, will change when you move from one place in an orbit into another place into the orbit in the gravitational field. So instead, what we've got to do is we've got to remember what our definition of gravitational potential is. So gravitational potential is the work done per unit mass in moving an object from one place in the field to another place in the field. So what you would do is you would work out your potential difference, then you would multiply it by the mass of the object, and that will give you your overall change in gravitational potential energy. So you'll notice that you can work out the new gravitational potential when it's now in orbit by doing V is equal to minus gm over r. Now again, remember this minus value is just indicating that as an attractive force of gravity acting towards the center of the center of mass of the object producing the gravitational field, but it's nothing to worry about. So we do V is equal to minus gm over r, work it through now, and we get our value to be 9.41 times 10 to the 6 joules per kilogram. Now we know previously that the gravitational potential at the surface of the Earth was 6.26 times 10 to the 7 joules per kilogram, so therefore you can work through the difference by doing 6.26 minus 0.94 times 10 to the 7. Now remember that's because 9.46 times 10 to the 6 is equal to 0.94 times 10 to the 7. So that gives us our potential difference. We then multiply by the mass of the satellite, 1,200 kilograms, to get our overall change in gravitational potential energy of 6.38 times 10 to the 10 joules. Now it talks about the next question about what's happening in the orbital motion of the satellite when it's used to place the satellite into an orbit with a longer period. Now what you've always got to remember is when we're considering satellites, we know that t squared is directly proportional to r cubed. So therefore, if t is getting bigger, r must be getting bigger. Now if r is getting bigger, that tells us that there's a greater amount of the energy store of the orbiting body going into the gravitational potential, so therefore there's less in the kinetic energy store of the orbiting body, so therefore its velocity as it orbits is getting smaller. So therefore you could also say it, because we know from circular motion that for a constant value of f, that v squared is directly proportional to 1 over r. So that's another reason why the velocity is getting smaller. Next question. Derive an expression to show that satellites in a circular orbit follow the equation t squared is directly proportional to r cubed. Next, Pluto is a dwarf planet and the mean orbital radius of Pluto around the Sun is 5.91 times 10 to the 9 kilometers compared to a mean orbital radius of 1.50 times 10 to the 8 kilometers for the Earth. So calculate in years the orbital period of Pluto. Then a small mass is released from rest just above the surface of Pluto with an acceleration of 0.617 meters per second squared. Assume that Pluto has no atmosphere that could provide any resistance to motion. Calculate the mass of Pluto, where the radius of Pluto is 1.19 times 10 to the 6 meters. So pause the video now, then unpause the video when you want to go through your answer. Well, it's very important that you can derive t squared as directly proportional to r cubed. So how would you work it through? Well, you've got to remember that the object is moving in orbit due to the gravitational force, so you say F is equal to gmm over r squared, but also it's the centripetal force because it's caused to move in a circular path, so therefore we can say that it's equal to m omega squared r. So therefore you can equate the two and say m omega squared r is equal to gmm over r squared. The small m's cancel through. Then we can also say that omega is equal to 2 pi over t, so we can pop t into the equation there, so we can therefore say r times by 2 pi over t all squared is therefore equal to g big M over r squared. You would then rearrange and collect the values of r, which are on both sides of the equation, so it becomes r cubed. So therefore we get t squared is equal to 4 pi squared over gm times by r cubed. So we know that g is a constant. In this case, big M, which is the mass of the object produced in the gravitational field, is a constant, and 4 pi squared is a constant. So therefore t is directly proportional to r cubed. You've really got to be able to remember how to derive that. Now the next question is you're going to then use this as a ratio. So what you can say is, you can say that Tp over Te squared is equal to Rp over Re squared. Now you are given in this question the value of Rp, which is going to be 5.91 times 10 to the 9. You're given the value of Re, 1.5 times 10 to the 8. Now again, you might think it's kilometers, do I need to convert it to meters? Well, because we're ratioing them in this equation, you don't need to. Now we also know that the answer we need to get for Pluto, it needs to be in years, so we can use the time period for the Earth's orbit in years, which is 1. So therefore we can say Tp over 1 squared is equal to 5.9 times 10 to the 9 over 1.50 times 10 to the 8 cubed. You know all the values apart from Tp. You make Tp the subject, you work it through to be 247 or 250 years to two significant figures, which is an important answer there, getting it much larger than the value of the Earth, so it makes sense. Now this next question, how can you work out the mass of Pluto? Well, what you can say is, we know that from our previous work that gravitational field strength is equal to G big M over r squared. Now again, big M is going to be the mass of Pluto. So what you can do is rearrange this and make Pluto make the mass of Pluto the subject. So you'd say big M is equal to G r squared over big G. Pop in all your numbers, and you know what G is, which is going to be the gravitational field strength, which is just the acceleration due to gravity, which is 0.617. Remember, it's always important to know that the gravitational field strength can also be called the acceleration due to gravity. You know what r squared is because you're given in the previous question, and you know what big G is because it's the universal gravitational constant, and you get 1.31 times 10 to 22 kilograms. Why do you give your answer to three significant figures? Well, in the question you were told you got an acceleration of 0.617 meters per second squared, which is three significant figures, so you give your answer to three significant figures. So I hope you've enjoyed this particular revision session where we have looked at different questions to looking at gravitational fields in AQA A-Level Physics. Thank you very much for watching and have a lovely day.